This is Design Safe Radio, where natural hazards researchers strive to make our society more resilient to everything nature throws at us.
What kind of data are you looking for, and what kind of sensors are you using for that? I mean, you've got miles and miles of cabling going through this thing.
A marathon length. I could start, and Ben could enrich that. But I mean, yeah, with our shake table facility, at least in this particular specimen, we've installed 750 sensors. About 250 of those are accelerometers. They're unidirectional accelerometers. They use a MEMS technology.
What's MEMS
for them? Microelectrical mechanical system. We have about 130 strain gauges, 350 direct displacement sensors. Some of those are a little spring-loaded. Others are linear variable transducers, but they're all uniaxial displacement sensors. We have a distributed GNSS system. We've got more than I'm sorry about the acronyms. It's a GPS, global navigation satellite systems. We're using the satellites to capture with receivers and
with receivers and at the bottom and the top and all that. Yeah.
Cool.
That's direct. That'll give us direct displacement, right? Because you've got a reference station and we've got receivers distributed up the height and on the roof of the system. As long as we have a clear day, which we hope we can, we hope we've laid them out. Yeah. We did a similar thing in Tallwood and gave us some good information, particularly at the roof, right? The satellites are quite visible at the roof of a tall exposed specimen like this. There are more than 50 digital video cameras of different technologies distributed in the building. Most of these are the site has done a terrific job of synchronizing these with the trigger to the shake table. So that means now a good number of them are like just typical GoPros. We'll turn them on, the facility will lift the table for us, and then we'll turn them off at the end. We'll have to go find, the short segments of shaking, which we're interested in. But a good number of them, almost 50 of them, are synchronized completely with the trigger of the shake table, which is really great because that means that our analog measurements, our direct displacement or our direct acceleration, will be triggered with those video feed views. We've also got some really great partnerships with the California Strong Motion Instrumentation program. So that's a largely distributed through the state of California. We have there are thousands of buildings that are instrumented with very high fidelity accelerometers, and we reached out to them and they came out and installed. They've got 33 additional accelerometers that are part of their program installed in the building. And then we've got a partnership. So that's California state funded. That's just another partnership that has come to the opportunity to invest in enriching with measurement potential for this program. And then we've got a partnership with CalTech, and they've developed over the years. They've developed some really low cost Raspberry Pi based triaxial accelerometers. They're very inexpensive, and they call their network the Community Seismic Network, or CSN. There, I thought about the acronym, sorry. And they were able to come out and install 75 of those throughout the building, and places that we couldn't enrich. So a little bit of overlap with the California Strong Motion Instrumentation program and our own use of our own sites, unidirectional sensors. But having that overlap and additional enrichment, we were able to put more of those sensors. They're really lightweight. I don't have one because they're all out in the building and all installed as of we speak today.
They're literally using every sensor that they have there, much to Kurash's chagrin.
Yeah,
that's what they're for, right? That's what they're for.
Yeah,
he's been really great with us.
There's other cool stuff too, like Tara's done a lot of work with drones in previous technology. So we've got UAVs flying around measuring the displacements of everything, and all these sensors. One chunk of them are helping us solve the questions we have about the structure itself, the structural questions, how the shear walls are behaving, et cetera. And then there's a whole nother fleet inside everything she described that are doing the heavy lifting of helping us figure out what's going on with functional recovery or damage that occurs as the earthquakes become greater and might make it difficult for you to use the building. So there's water sprinkler pipes and gas line pipes and ceilings installed with different details. And there's a whole collaboration that is looking at that whole non-structural aspect of the performance of the building as well. And that's, I don't know, how many of this, that's like 250 of the sensors or something like that, kind of focused on those questions.
Wow.
So it's not something in
Yeah,
that neighborhood.
yeah, it's almost half of the sensors
Yeah.
actually.
Okay. So I mean,
because
it's
there's a little bit of overlap and things like that. We had to
Yeah.
make decisions and things like you give priority to structural instrumentation, but then you know that kind of if you want to understand the interaction, we have an fully operable, resilient stair system throughout the building that went in modular components, and that kind of the behavior of what that subsystem might be and how important it is. And we have some experience working with the manufacturer designer of that stair system, and so there's some modifications to kind of tease out what we think might happen to that system. But then you need information from the primary structure, and so there's a bit of overlap there in some of the sensors that we chose.
Yeah. So you're measuring how far the building moves, how fast things move, and then the rate of change of those, acceleration. You're measuring stress indirectly, the internal resistance of the material to these applied forces, and the strain, which is how far it deforms under stress, and all sorts of really fun engineering things that I'm trying to remember from my long time ago.
Doing a good job there.
Yeah. It's just amazing the types of things that you can measure and in real time as well. I mean, you've got this all hooked up to a data acquisition system. Did you guys do a hybrid simulation with this? I'm trying to remember beforehand at some of the smaller scales.
Well, some of the components were tested, using simulated seismic loads. I mean, even at Johns Hopkins, Ben's team, looked at repeating cycles, even at the connection level. And then here we looked at walls and wall lines. But you try to replicate that by putting the actuator somewhere else. And then, that kind of creates the boundary condition to recreate something, and then you have to imagine you've got something else connected to it, right? You can imagine that the steel sheathing and the fastening is connected to something else and recreate the boundary conditions. So you can do a lot of those, do a lot of connection tests, or you could do, hopefully a moderate amount of, wall or wall line tests. Because as you go up, the cost of the experiment becomes greater and you have fewer and fewer you can do until you get to this point where you're performing a landmark test like this and you can really only do one. So you really have to think about the whole protocol really carefully and try to optimize what you can get out of it.
Yeah, and this will not only inform all the things that we've talked about before, but validate all the previous experimental methods and models and improve those for future work.
Yeah, I just wanted to ask that in terms of like the idea of hybrid, like when we think about it as structural engineering experimentalists and testers, we have a very specific idea of using a simulation to drive the loads that you put on the structural. So, but there's another sort of aspect of hybrid that I think is sort of more generally interesting. So that 10-story building that's behind you is actually just a slice of a large building that we actually designed, which was a full construction. And then we had to turn it into what we could actually test, right? So this is a hybrid component of a full-scale 10-story building, which would have a much larger footprint as well. So even as big as the facility is, of course, buildings themselves are bigger.
Yep. You can always build it bigger. We can't build the Burj Khalifa on top of this. Not yet, anyway. So when are you expecting to have some test results that you can share, and what are you hoping to see out of those?
Well, I think, there'll be some immediate, like visible learnings, and those, I think as a research team group, just as a researcher in general, you want to try to expose those, let's say, first order or, observations as efficiently but carefully as possible. So, with the first check will be, did we kind of see the damage to the shear walls that we anticipated and we've seen in component tests? And those are kind of, immediate tier one reports, I think we could collectively come together. We've already put ourselves on the hook as a team to get out some conference papers, local conference, the Structural Engineers Association of California, and we're going to talk about that in September. Got an opportunity to get an abstract in for that, and then each of the team is trying to work on their respective areas. The element of functional recovery led by our NIST scholar, trying to get that word out as quickly as possible. And I think those immediate, observations will come out in the first, weeks and months after the tests. I think the longer term implications are like the work that folks need to do at the codified level. The archival publications really need to come out to very carefully document the path to get to those conclusions. I mean, ultimately, as a research team, our requirement is to physically release the data publicly because it's been, as a seed funding, National Science Foundation funded. And so we know in our mind that within 1 year, we've got to get our data archived into your database. So we know that. I've had experience doing that and just helped the Tallwood group do that within its 1 year limit. So, but that's at the science level. That's very, so, it really depends on the context to your question.
Yeah.
But we are definitely reaching out to and have the opportunity within the first few months to get the first order impressions out to the community regarding the behavior of the structural system as a whole and the functional nature of the different subsystems. Those will come out immediately because those are solid state. We know what those observations are going to be. And then there's going to be a lot of art and nuances to processing the data that we'll need to do really carefully. And knowing instances of damage and shear wall distortions, which caused led to propagation of elements. Boy, that's a lot of data to study. And you started this off with how many channels do you have and things like that. So as a research team, we'll have to dive into those a lot deeper before we give the nuances. And then model validation. I mean, there's some really great finite element models that were used for the pretest efforts here. Real high fidelity models and say maybe more design community level models, and validating those. The students that are going to get their PhDs along the journeys of those couple of models are they're going to want to go back right away, but they need to know that the data that they're using in order to compare to their response predictions is robust. So that'll take a little bit of time too, but they've been doing amazing balancing all the demands on the pretest side. So I have the feeling that they'll be able to, pretty efficiently within the first, 6 months or so, get back in and put the achieved, input excitation in and see what their models spit out.
Yeah, I would just add kind of big picture, people see like construction engineering or structural engineering technology like this, and then we talk about how long it takes for it to get adopted. And folks can get a little dispirited, like it's going to take 10 years to get into the codes, and then 20, so the timelines can seem really long. There's one way that there's a workaround for that, which is performance-based seismic design and peer review. So a lot of the really amazing structural engineering technologies that have come into the earthquake engineering community have happened primarily from California structural engineers. And someone has an understanding of a new technology, wants to put it in a building, and then they develop a peer review process where other structural engineers work with them to independently agree that we can make this advancement, even though the code doesn't have a line specifically that says you can do this specific thing. And what's exciting about that kind of peer review is this sort of testing is the kind of landmark work that a peer review team can rely on to sort of everyone agree that, okay, our models are doing what they want, and we believe you can make these technologies. One of the partners on the team is already looking at doing high-rise cold form steel in as soon as a few years from now, already in the planning stage, that is well beyond the code, sort of looking at using that kind of peer review process. So there is ways that our field takes these technologies and gets them adopted quickly. The long path where it just gets into the code is a line, that so every single engineer can use it does take a little bit longer. But I think if you look at the history of the table, you can see work on various dampers, bulk and restraint braces, all these specific technologies that peer review teams like that have been using to use in California construction and high seismic construction all on the West Coast for decades now. All post Northridge 1995 earthquake solutions. So happy, thrilled even to be a part of that sort of lineage as we work on this technology.
Yeah, it's really important and encouraging. As I was on actually getting interviewed on another podcast yesterday, the disaster podcast. Shout out to those guys, Jamie and the crew, about just what it takes to get this research into practice. And it's always encouraging to see this. Yeah, there's more than one way. Not just getting it into code, but also that peer review process through earthquake and civil engineers that is an important part of that.
Thanks for listening to today's episode of Design Safe Radio. Be sure to like and subscribe on whatever platform you happen to be listening to this on. It really helps people find our show. Thanks to our amazing sponsors, the National Science Foundation and the NARI Network Coordination Office, which is award number 2129782. Big thank you to Marty LaChance, our guest booker and topic researcher extraordinaire, and Raquel Ruiz, who is our video and audio editor. I'm your host and NARI Facility Scheduling and Operations Coordinator, Dan Zahner. We'll see you in the next episode. Until then, stay resilient.